Hello everyone, I'm Reshma. In this video, we're gonna discuss about RAID levels from operating systems. Before we jump in, don't forget to give this video a big thumbs up if you enjoy it and feel free to leave any comments or questions down below. First, let us understand about what is RAID and then we get into the RAID levels. So, RAID means redundant array of inexpensive disks. It is a technology that combines multiple physical drives into a single logical unit for data redundancy, performance improvement, or both. Different RAID levels offer various combination of performance, redundancy, and capacity. RAID seems improve performance and improve the reliability of storage system by storing redundant data. RAID is widely used in server environments, data centers, and enterprise storage systems to enhance data integrity, availability, and performance. The specific RAID levels chosen depends on requirements of the system or application. Balancing factors such as performance needs, fault tolerance, and cost consideration. In this video, we're gonna discuss about 9 RAID levels which are shown here. The first one is RAID 0. RAID 0 stands for Redundant Array of Independent Disk Level 0. RAID 0, also known as data stripping, involves splitting of data into small blocks and spreading it across multiple disks in a way that allows for simultaneous read and write operations. In this configuration, each disk contains a portion of the data and data is written to and read from the disks in parallel. RAID 0 doesn't provide fault tolerance as there is no redundancy or backup copy of the data. If one disk fails, all the data on the array is lost. If we look into the picture, here there are two disks and the data is stripped into the two disks. This is RAID 0. RAID 1, also known as disk mirroring, involves the duplication of data on two or more disks. In this configuration, all the data is written to or more disks simultaneously so that each disk contains an identical copy of the data. This provides fault tolerance, as if one disk fails, the system can continue to operate with the remaining disks until the failed disk is replaced.
RAID 2 Memory Style Error Connecting Codes. RAID 2, which is rarely used in practice, strips data at the bit rather than block level and uses a Hamming code for error correction. The disks are synchronized by the controller to spin at the same angular orientation, so it generally cannot service multiple requests simultaneously. However, depending with a high rate Hamming code, many spindles would operate in parallel to simultaneously transfer data so that very high data transfer rates are possible. In RAID 2, data is divided into individual bits and then stripped across multiple disks with a dedicated parity disk that stores the parity information for all the data disks. Whereas the parity information is generated using Hamming code, which allows for single bit error correction and double bit error detection. This means that if a disk fails, the data can be reconstructed using the parity information from the dedicated parity disk. For example, in the Thinking Machines data vault where 32 data bits were transferred simultaneously, the IBM also observed a similar usage of Hamming code and was capable of transmitting 64 data bits simultaneously along with 8 ECC bits. With all hard disk drives implementing internal error correction, the complexity of an external Hamming code offered little advantage over parity. So RAID 2 has been rarely implemented. It is the original level of RAID that is not currently used. RAID 3 Bit Interleaved Parity. RAID 3, which is rarely used in practice, consists of byte level stripping with a dedicated parity disk. One of the characteristics of RAID 3 is that it generally cannot service multiple requests simultaneously, which happens because any single block of data will be spread across all members of the set and will reside in the same physical location on each disk. Therefore, any input-output operation requires activity on every disk and usually requires synchronized spindles. In RAID 3, data is stripped across multiple disks with one dedicated parity disk that stores the parity information for all the data disks. Unlike RAID 2, the data is not divided into individual bits but rather into larger data blocks. This means that if a data disk fails, the data can be reconstructed using the parity information from the dedicated parity disk. This makes it suitable for applications that demand the highest transfer rates in long sequential reads and writes. For example, uncompressed video editing. Applications that make small reads and writes from random disk locations will get the worst performance out of this level. RAID 3 was usually implemented in hardware and the performance issues were addressed by using large disk memories. RAID 4 consists of block-level stripping with a dedicated parity disk. As a result of its layout, RAID 4 provides good performance of random reads while the performance of random writes is low due to the need of writing all parity data to a single disk unless the file system is RAID 4 aware and compensates for that. In this level, entire set or block of data written onto the data disk and then the parity is generated and stored on a different set of disks. This level overcome at most one disk failure. If more than one disk failure occur, then there is no way to recover the data. Both RAID 3 and RAID 4 require at least 3 disks to implement RAID. An advantage of RAID 4 is that it can be quickly extended online without parity recomputation as long as the newly added disks are completely filled with 0 bytes. In diagram 1, a read request for block A1 would be serviced by disk 0. A simultaneous read request for block B1 would have to wait, but a read request for B2 could be serviced concurrently by disk 1. RAID 5 Block Interleaved Distributed Parity. RAID 5 consists of block level stripping with distributed parity. Unlike in RAID 4, parity information is distributed among the drives. It requires all drives but one be present to operate. Upon failure of a single drive, subsequent reads can be calculated from the distributed parity such that no data is lost. RAID 5 requires at least 3 disks. RAID 5 requires 3 drives, stripping the data across multiple drives like RAID 0, but also has a parity distributed across the drives. In the event of a single drive failure, data is placed together using the parity information stored on the other drives. There is zero downtime. Read speed is very fast, but write speed is somewhat slower due to the parity that has to be calculated. It is ideal for file and application servers that have a limited number of data drives. There are many layouts of data and parity in the disk drive of RAID 5 array depending upon the sequence of writing across the disk. That is, the sequence of data blocks written left to right or right to left on the disk array of disk 0 to n. The location of the parity block at the beginning or end of the strip. The location of the first block of a strip with respect to the parity of the previous strip. In comparison to RAID 4, RAID 5's distributed RAID 6 block interleaved with two parity bits. RAID 6 extends RAID 5 by adding another parity block. Thus, it uses block level stripping with two parity blocks distributed across all member disks. RAID 6 is just like RAID 5, but the parity data are written into two drives. That means it requires at least 4 drives and can withstand 2 drives dying simultaneously. Read speed is as fast as RAID 5, but write speed is slower than RAID 5 due to the additional parity data that have to be calculated. RAID 6 is a very good option for a standard web server where most of the transactions are reads. But it is not recommended for a heavy write environment such as a database server. As in RAID 5, there are many layouts of RAID 6 arrays depending upon the direction of the data blocks are written, the location of the parity blocks with respect to the data blocks, and whether the first data block of a subsequent strip is written to the same drive as the last parity block of the prior strip. According to the storage networking industry, the definition of RAID 6 is any form of RAID that can continue to execute read and write requests of all RAID arrays, virtual disk in the presence of two concurrent disk failures.
Apart from the RAID levels which are discussed above, there are some combination levels also in the RAID. The combination levels refers to RAID configurations that combine elements of different basic RAID levels to achieve specific performance, redundancy, or capacity goals. Two common combination levels are RAID 10 and RAID 01. Let us discuss about RAID 01, which is also called RAID 0 plus 1, which means arrays implemented as RAID 1 whose elements are RAID 0 arrays. Such implementations has the benefits of RAID 0 speed and RAID 1 safety. RAID 0 plus 1 is a RAID level using a mirror of stripes, achieving both replication and sharing of data between disks. The usable capacity of RAID 01 array is the same as RAID 1 array made of same drives, in which one half of the disk is used to mirror the other half. RAID 10 is also called 1 plus 0 and sometimes 1 and 0. Is similar to RAID 01 with an exception that the two used standard RAID levels are layered the opposite order. Thus, RAID 10 is a stripe of mirrors. A RAID 10 array is implemented as RAID 0 whose elements are RAID 1. It combines the same advantages of RAID 0, which is speed, and RAID 1 safety, but in a different way. After the failure of a disk while it is being replaced, only the tiny fragment of a whole array is rebuilt. Unfortunately, it has same drawback as that of 01, the cost of implementation. Coming to the end of our video, we have given brief notes on every level so that you can understand better. Pause the video and read them. I hope you have learned something from this video. If you have any doubts, comment below and don't forget to like this video.